So welcome back to lecture 5 of Digital Systems 1, and in lecture 5 we shall be covering Boolean algebra. So lecture 5 comes from chapter 4 of the book. In fact, it comes from the first 7 sections of chapter 4, and we'll be looking at section 4-1, which talks about Boolean operations and expressions, section 4-2, which talks about laws and rules, algebraic Boolean algebra, laws and rules, and then we'll look at De Morgan's theorem, and then section 4.4, which is Boolean algebra analysis and logic circuits. We'll look at how to use Boolean algebra to simplify logic circuits, and we'll look at standard forms of Boolean expressions. And then later in section 7, we'll look at Boolean expressions and the truth table. Zooming into Boolean operation and expressions. In this unit, the student is expected to be able to define what a variable is, to define a literal, identify sums and products, be able to evaluate sum and a product, and be able to explain Boolean addition and multiplication. So first of all, let's explain some basic terms. A variable in Boolean algebra, it's a symbol which is represented by a letter, and this symbol represents an action, a condition, or a piece of data. So a Boolean variable can have two values, either of the two values only. It can either be 0 or 1, or it can be low or high, it can be true or false. Like any algebraic expression that you would have known, a normal mathematical algebraic expression or variable, but in this case it's restricted to just two values. And then the other important definition here is a complement. A complement is normally an inverse of a variable, which is indicated by an overbar. For example, a bar is the complement of a. So if the value of a is 0, then a complement is 1. Another common term used is called a literal. So you might come across a term called a literal. So whenever a literal is mentioned, it refers to a variable or its complement. You would have realized from the previous lecture where we explained the function of a logic gate that the Boolean addition behaves like an OR function. So it's equivalent to an OR function. What this means is that if you see a Boolean expression 0 plus 0, then the result is going to be 0. So it's treated as 0 or 0. And then if you see an expression 0 or 1, then the result becomes 1. And so on and so forth. So if you have 1 or 1, then the result becomes 1 as well. So the addition, in this case for Boolean algebra, is treated as an OR function. So for example, if you have an expression or an equation here, a Boolean algebra equation with variables a, b, c, and then you have a complement plus b plus c is equal to 0. One of the cases that can satisfy this equation is when the values of a is equal to 1, when the value of b is equal to 0, and c is equal to 0. So this is just one of it. What it means is, in this case then, the expression would be in such a way that you have a complement is 0, or B in this case would be 0, C would be 1. So because now you have 0 or 1, because you have a 1 this side, we know that the OR gate will give us a 1. So contrary to that, Boolean multiplication is represented by an AND function. So according to the behavior of the AND function, we know that the AND function, the output of the AND function is high only when both of these inputs are high, which therefore means that if you have a 1 multiplied by a 0, then you will always have a 0. That is, if either of those other operands are 0, then you will have a 0, except the case where you have both the operands as 1. Then it means, if you look at an example here of an expression whose result is a 1, it therefore means then that in this case all of these literals have to be 1, which means A complement has to be 1, B complement has to be 1, C complement has to be 1 in order for this expression to be 1. Which means in terms of the variables, then B straight becomes 1, C becomes 1, and A will therefore become 0, so that it's a complement, it's 1.